Back, and we're on 5.3 part 4, the fundamental theorem of calculus part 2. If you recall, the last theorem, part of the theorem that we talked about, was the fundamental theorem of calculus part 1, where we basically said that g prime of x is equal to the integrand, and then we dealt with chain rule in case the limit of integration was not x, but was some other function of x, we had to take the derivative of that as well. So now, with the next part, we're talking about how we're dealing with a definite integral. So if f is continuous on the closed interval a, b, then we have the integral from a to b of f of x dx is equal to capital F, some antiderivative evaluated at b, minus capital F, the same antiderivative evaluated at a. And so the evaluation, you might think, well, what happened to the c involved in the indefinite integral? If you look at it, oh, there's one more statement here, sorry about that, where f is any antiderivative of f that is a function such that f prime, remember, has to equal the function lowercase f. So in words, what we're going to say is if we know, and I'm going to write this out pretty quickly, but if you need to stop the video, you can stop the video when I'm done. If we know the antiderivative, f, capital F, of the lowercase function f, then we plug in the endpoints a and b and subtract. Note the arbitrary constant found in the indefinite integral, the plus c, cancels. So we get this. We get f of b plus c, regardless of what the c is. It's then minus capital F of a plus c, which is just capital F of b minus capital F of a. Boop. C's cancel. So let's try a problem. Use part 2 of the fundamental theorem of calculus to evaluate the integral. So recall, though, as we go through these, I want to just tell you that each time we look at an integral, I'm going to remind you that this is some antiderivative evaluated at 1 minus the antiderivative evaluated at 0. So let's go ahead and do this. So we get the antiderivative of x squared. We already know from section 410. You'll be reviewing some of your notes from 410, the antiderivatives. So we have x cubed over 3. And then we're going to put a bracket on the right-hand side, and we're going to say from x is equal to 0 to 1. So then we evaluate the antiderivative as 1 cubed, here's the antiderivative evaluated at 1, minus the antiderivative evaluated at 0. So we get, for an answer, we get 1/3 minus 0, which you know we recall from using the calculators that we got the integral of x squared dx from 0 to 1 is equal to 1/3. Okay, so again, working on antiderivatives. So we're on example 7, number 2. We have the integral from 2 to 8 of 4x plus 3 dx. So we're going to evaluate an antiderivative evaluated at 8 minus the antiderivative evaluated at 2. So recall that your antiderivatives, so let me put this over here. That's better. So this is equal to then, we're going to take the antiderivative, so we get 4x squared over 2 plus the antiderivative of 3 is 3x. Put the bracket around, and we're going to say from x is equal to 2 to 8. So we're going to take the antiderivative, which is 4x squared over 2, and we're going to cancel. We're going to simplify this a little bit. So it's going to give us then 2 times 8 squared plus 3 times 8. And then we're going to subtract 2 times 2 squared plus 3 times 2, evaluating the integral, the antiderivative at 8 and then at 2. So we end up with 2 times 64. Oops, everybody makes those kind of mistakes sometimes. 64 plus 24 minus, this is going to be 2 times 4 is 8, minus 6. So we get 2 times 64 is 128 plus 24 minus 8 minus 6 to get a grand total of 138. Let me just check my math there real quick. Okay, and it checks out. So we have the integral from 2 to 8 of 4x plus 3 dx is equal to 138. Now, it's interesting, we have the calculator on, so we might as well go ahead and check this one. So we go to y equals, we don't have the calculator on, but here it goes. So we're going to go to y equals, we're going to clear out our function, if we have anything in there, and we're going to type in 4x plus 3. 4x plus 3. And you might be wondering, well, Mrs. Allen, we can even use geometry to find this. We're going to hit zoom 6, make sure we're on a standard screen. So I'm going to go from 2 to 8. So in that case, I'm going to take my window up a little bit higher. I'm going to take my y max to, let me see, 8 times 4 is 32. So I'm going to take it to 50. 50, just to make it, get it really high up there. Okay, so we're going to hit second, trace, 7, the lower limit is 2, hit enter, and the upper limit is 8, hit enter. The area that you see is 138. Okay, awesome. So using the fundamental theorem part 2 is taking the antiderivative and evaluating it at the upper limit and the lower limit and subtracting. So recall with our think cycles, we have cosine. So if I want to find the antiderivative of cosine t, recall that whatever that is, the derivative, if I'm going this way to find the antiderivative, the derivative of whatever I need is going to be cosine. So we know that's sine t. So here we have then the antiderivative of cosine is sine t. And then we're going to put the bracket on. We're going to evaluate from t is equal to 0 to pi over 2. So we end up with the expression sine of pi over 2 minus sine of 0. And we end up with 1 minus 0. Sine of 0 is 0. Sine of pi over 2 is 1, so we get the answer 1. So we have the integral from 0 to pi over 2 of cosine t dt is equal to 1. It's a pretty cool number when you think about the cosine graph. When we're talking about the area of a function going from 0 down to pi over 2, so we're talking about this area where we're up at 0, 1, and we go to pi over 2. We're at the point pi over 2 is 0. So it's this area. I think that's really cool. It ends up to be unity. Okay, so let's try example 8. Example 8, examine the following problem to find the error. So pause and see if you can determine what the error is in this problem. Okay, and I'm hoping you found it, but I'm not sure that you did because all of the math looks correct. So here's the problem. FTC, if you notice we're going from -2 to 3 of x to the -5th. How about if we rewrite, just as an aside, we'll rewrite our integral and maybe you'll see clearly what the problem is. From -2 to 3, we have 1 over x to the 5th dx. So what I would look at is domain of this function and see if there would be a problem. And certainly we can say that x cannot be 0. And if you've noticed, we're going from -2 to 3, and clearly from -2 to 3, -2 to 3, 0 lies between there. So that's where you're going to have that asymptotic behavior. So FTC applies only to continuous functions on the respective interval from a to b, and that would be a closed interval from a to b. So that is infinite discontinuity at x is equal to 0 for this particular function. Okay, so we have a Fresnel function, and that's kind of an interesting function. I'm going to let you study this, and I want to talk a little bit about this, but I want you to look up the results of the Fresnel function and maybe how they're used for highways and railways, and maybe even with optics. So we'll get back to you. That's the end of this video. Have a good day.